Hello learners, greetings of the day. The course title is Renewable Energy, Technologies and Their Uses, and the lecture topic is Fundamental of Solar Building and Design. Myself, Dr. Rohit Tripathi, Assistant Professor, JC Bose University of Science and Technology, YMCA Faridabad. When I start about the building design, then the first thing in mind, what is the building? So we have seen there's a lot of building around us. So when we are talking about a solar building, then a solar building means a comfortable that gets at least part of its heating, cooling and lighting energy from the sun. Can be designed to use sun irradiance, building material and other supports to create human comfortable and low energy consumption green building. Solar design incorporates feature in building and its natural surroundings that harness the sun low rays in winter and deflect the sun high rays in summer to naturally warm and cool the interiors. A building's orientation, elevation, room layout, materials and surrounding outdoor landscaping all contribute to its solar design. It incorporates the use of windows, walls, floors to collect, store and distribute solar energy in form of heat in winter and block solar heat in summer. If we talk about the classification of building design, then there is a three types of building design. First one is passive system, passive building design. Second one is hybrid building design and third one is active building design. If we talk about the all three systems, then passive building design is a very popular in nowadays due to it takes heating as well as cooling. If we talk about the passive system, then energy collection and storage by natural means. It means energy distribution is also by naturally. The system mostly works without external power. Daylight is extensively used for passive building system. Passive cooling and heating can be inherent in the building construction and energy flow by natural mean or natural process. If we talk about hybrid system building design, then energy collection and storage can be naturally. Energy distribution from collector to store or from storage to living space in by mechanical means. The system uses external power in hybrid building design. In the same, daylight is also extensively used in hybrid system. Passive cooling and heating can be inherent in building construction design for hybrid building design. When we are talking about the active building design, here energy collection and storage is by forced means there are some external force is required to build a active building design. Energy distribution by force also. The system works with external power, which I have already told you. Less use of daylight is required for active building design. Heating and cooling system and their control are not an integral part of building construction. Energy flow within the system is by force only. So these are the three different types of building design: passive, hybrid and active. If we talk about the basic classification of any solar building system, that is the three types, three classifications are there. First one is passive or active solar heating. Second one is passive and active cooling. And third one is daylighting. Solar heating building design. If we talk about the heating building, then there are two types of building design: through direct gain or indirect gain. If I talk about the direct gain, then there are three systems from which we can obtain the direct gain from the sun. First one is window skylight, second one is living space, and third one is walls and floors. If we talk about the indirect gain, that is glass wall over the existing walls. Second one is living space and third one is concrete water filled wall. So such type of solar heating can be classified in all these types. If I talk about the solar heating only, then there is some element of the solar heating, that is collector space and thermal mass. We will discuss this later on in this lecture. If I talk about the solar cooling, then there is a three different classification about the solar cooling. First one is sky, second one is atmosphere, and third one is ground. If I talk about the sky, then the radiation can be obtained, or by radiation we can obtain such type of system. If I talk about the atmosphere, then convection evaporation is required. If I talk about the ground, then the conduction is required. When we are talking about the solar cooling, then shading devices is also required, trees or some shading is required, insulation and evaporating cooling. But when we are talking about the solar cooling, then the one thing must be in our mind: the goal in solar building is optimum balance of mass, glass, insulation for a particular site and house design. The third thing of solar building design, that is the daylight. So we can obtain the daylight from some window or lights, from natural lights, and we can obtain such daylighting from some reflector also. So by arrangement of such thing, we can obtain daylighting from the sun in a house or building. Before going to further design, we have to think about some points that must be in our mind. It must be clearly understood that passive design is not a style of building or a package technological system that can be plugged into any building type. Second point must be in there. Passive design is determined by how a building works to store and give off heat from the sun, and how it cools and provides ventilation. Next, passive design represents a sophisticated response to the environment. And the last point will be solar active system can be integrated into the building depending upon the requirement and availability of sunlight space. And there is some specific step to design a building. There is a 7-step when we are designing a solar building. Then that 7-step must be followed in a sequence. If I talk about the step 1, then the identification of comfort need regarding temperature, humidity, fresh air and light intensity, as well as identification of climate resource and constraints like wind, solar, radiation, humidity level and temperature, daytime and nighttime also. Step 2, identification of energy, design incorporating thermal aspects as well as luminous aspects. The thermal aspects include orientation, windbreak, reflector, sunscreen, greenhouse, insulation and so on. If I talk about step 3, then the identification of energy flow of the proposed design. If the design affects thermal energy flow, the specific type of flow as well as season must be identified. On the other hand, it can be said that if the system affects the lighting of the building, the source, direction and intensity of the natural light must be identified. If I talk about step 4 for designing, so estimating energy consumption is very important. Step 5, identification of solar active systems which can be integrated into the building to meet part load of energy requirements. Next, identification and evaluation of energy saving resulting from thermal as well as lighting considerations. And the last point is final point, that is evaluation of cost of proposed design. Thereafter, comparison of the cost of the design with resulting energy savings. So if we follow all 7 points regarding designing of any building, then our building must be optimized for solar system. Now I have told you all 7 steps for designing. All 7 steps can be introduced you in pictorial way or in diagram way. So if I talk about step 1, that is the identity of comfort of human. So there are some parameters which are must be in our mind, that is temperature, humidity, fresh air and light level. All 4 parameters must be in mind and that must be optimized during the design. Then some identify of the climate resource also, that is wind, solar radiation, heat, light, humidity, temperature, daylight and seasonal parameters. These are the step 1. If I talk about step 2, then all these points must be incorporated, where the orientation of windbreak, reflector, sunscreen, green home insulation, as well as windows, reflector and skylight. This is the energy conscious design. This is the step 2. If I talk about step 3, then the upper side of step 2, that is the thermal, and lower part of the step 2 is the daylighting purpose. So we can classify step 2 in thermal and luminous. So the output of the thermal goes for winter and summer, whereas the output for the daylighting, that is a clear and overcast. So first I talk about thermal in step 3, that is the winter. Winter and summer can be managed through radiation, conduction and convection concepts. By all 3 concepts we can optimize our winter and summer season. And if I talk about the luminous, then clear and overcast, that can be managed through some lux level within the room or building. Now I come on step 4, that is the calculate energy units. If we have designed some optimized solar building, then definitely we have to calculate energy units as well. So when we are going for some thermal point of view or electrical point of view, there is some energy produced in form of kilocalorie or kilojoule, and that can also generate by some thermal and electrical system. By generating this energy from thermal or electrical system, definitely we have reduced the use of fossil fuel like coal, oil, gas and other things. When we have calculate the energy units, then definitely we have to go for energy saving also. That is the step 6, calculate energy saving. So in step 6, we have to calculate what exactly energy we have saved. And the final last step, calculate the cost benefit. We have to calculate the cost benefit through cost of design as well as compare the cost of design with benefit. So if I have told you step by step and pictorial view of system design steps. Now thermal energy flows. We are talking about thermal and electrical as well. When we are talking about the thermal, then thermal energy is required to calculate through some parameters. First one is conductive heat transfer. The conductive heat transfer can be represented by a relation, that is Q equals to capital U A TW minus TC, where the Q is rate of heat transfer in watt per meter square, where the U equals to overall heat transfer coefficient of the material through which heat is conducted. A is cross sectional area of material, where the TW equals to temperature of air next to the warmer surface, where the TC is temperature of the air next to the cooler surface, and the temperature is in degree centigrade. The temperature heat transfer coefficient U depend on the conductivity of the material, and thickness of material is given by some expression. That expression is 1 upon U equals to 1 upon UT plus 1 upon K upon L plus 1 upon UA, where the K is thermal conductivity of the material, UT is inside heat transfer coefficient of watt per meter square degree centigrade, UO equals to outside heat transfer coefficient, where the L is thickness of the material. Now, the thermal conductivity K of various building material is given in table, and it may be written in terms of thermal resistance capital R. Q equals to capital A TW minus TC upon R, where the R equals to 1 upon U. In this table, there is the different materials are here, and the respective materials has some thermal conductivity with the density and specific heat. Here I have mentioned some bricks, woods, glass, insulating materials and others. So from this table, we can calculate a particular material conductivity on the basis of density and specific heat. Then the next parameter is convective heat transfer. The conductive heat transfer is referred to the movement of heat through fluids or gases. It is associated with phenomena like infiltration, evaporation, cooling, etc. It is expressed as Q equals to HA delta T, where the Q is, small q is convective heat transfer rate in watts, where and small h equals to convective heat transfer coefficient capital A, that is the area of surface, and delta T is temperature difference of the surface and air in degree centigrade. The next parameter is radiative heat transfer. The radiative heat transfer takes place between two bodies and depends on the surface condition of both emitting as well as receiving surface. In fact, when thermal energy falls on surface, a fraction of its gets reflected and a fraction gets absorbed, and the balance gets transmitted such that like a given expression, that is alpha plus pi plus rho equals to 1, where the rho is reflectance of the surface, alpha is absorptance of the surface, and pi is transmittance of the surface. Now, thermal parameters has been completed. Now the terms comes is daylighting, and daylighting can be calculated on the basis of luminous energy flow. When we are talking about the daylighting, then lighting is responsible for about 10 to 18% of total residential energy consumption. Daylight can make internal lighting unnecessary during daytime. It is estimated that with the use of proper colors in the walls, energy efficient CFL, LED and daylight, the lighting consumption can be reduced significantly. Any improvement in window replacement and addition of windows, skylights and reflectors that can improve lighting quality in the room or building. Lighting energy needs can be decreased by about 20 to 40% simply by painting inside the walls white or light color. Daylighting is an environmental technology, and the concerned architect or designer must be able to analyze the performance characteristics of the system in terms of lighting, comfort, energy use and its cost. Now, next term is efficacy of the light source. It is also required. Luminous flux is the amount of light output from a source, and it is measured in lumen, LM. It is denoted by LM. The lumen output per watt of power consumption is known as efficacy of the lighting source. So by this efficacy, we can calculate exact luminous output of any power, or the lumen output received on a meter square of a surface area is referred to as lux. The efficacy of daylight even during overcast day is about 110 LM per watt, whereas for incandescent lamp it is 10 to 20 LM per watt, and for fluorescent lamp it is 55 to 90 LM per watt. If we talk about a solar building design in passive mode, there is a 5 different component of passive building design. I have shown one figure where we can see summer sun, winter sun. Here we can see what is the angle between these two seasons, and here I can see the position of sun is different for both seasons. And if I talk about the component, then window, control, distribution, absorber and thermal mass. These are the 5 different components of any solar building. If I talk in detail about all these 5 parameters or component, then a collector or aperture, it is a large glass area through which sunlight is allowed to enter the building, because this is the input area from where the sun rays comes to the building or room. Second is absorber. It is the dark surface of storage element that absorbs the solar heat, which produce some heating into the building. Third one is thermal mass, the materials that stores the absorbed heat. This can be materials such as a concrete, stone, brick or a water tank. Now, next point is heat distribution system. According to the figure, the heat distribution could be natural, using the concept that heat flows from warmer material to cooler ones through conduction, convection or radiation, which I have already told you in previous slides, until there is no longer a temperature difference between these two. This could be also be done with the help of fans, ducts or blowers to calculate the stored heat in active mode or passive mode. It depends. The next point is control or control mechanism. We can say this is needed to regulate the amount of sunlight entering the building or room. This can be simple as roof overhang designed to allow more sunlight to enter in the winter or less in the summer. I have given you one table. In this table, we can see some examples regarding all these components. The first component, which I have already discussed, aperture. If I talk about aperture, then definitely the window, cavity opening and other surface which is required. If I talk about the absorbing surface, then wall, floor, black metal, buffalo, barrel, dark hoses or pipes. Talk about thermal mass, then concrete, stone, brick, sand and water. Heat distribution, arrangement and coloration of interior panels, surface conduction, radiation, vents or ducts, interior wooden or doors, means some insulator or some insulating material is required. And the last is control or control mechanism, then roof and landscaping, window coating, covering, sunscreen, pergolas and shading. If I go in detail about all these parameters in a system or any design, then it must be required to discuss in detail all these components. If I talk about the aperture or window, then the correct size, number and type of window depends on climate or current climate. For climate that need heating, a southern exposure and windows that have large solar heat gain coefficient is recommended highly. SHGC, a value between 0 and 1 that measures the fraction of sun's heat passing through a window. It is also required. HSGC. Next is windows on the east, west and north side should have low SHGCs because they are primarily illuminated in the summer when heat gain is not required or wanted. Next is window need low emissivity coating. What is the emissive coating? Low E window limits the passage of heat by radiation, block interior heat from leaking to cold, block exterior heat from entering cool interiors. When I talk about the heat absorber, surface of the sunlight hits after it has passed through aperture. I have given one figure also. We can see in this figure the heat absorption surface. We have seen in this figure the bottom surface is highly coated or painted by a dark color, which absorb maximum gain from the sun. The floor surface could be tilt or a dark painted surface of a barrel, possibly holding water. Thermal mass, it allows radiant heat collected during the day to be stored and released gradually at night. The amount of thermal mass required depends on the required amount of heat that needs to be absorbed during the day and the light of the time to disperse. And the last one, if barrels of water can be used to thermal mass, because water has the highest specific heat of 1. Then heat distribution, which is also required. An effective design requires a means to deliver heat evenly throughout the house. This is accomplished by radiation from warmed surface, convective air movement through windows, doors or vents, directly by conductive across materials. A true passive design would incorporate an open floor plan relying on natural convection and radiation. Buildings with many isolated rooms rely on mechanical means for even heat distribution. Last one is control or control mechanism. Control mechanism regulate when and how much solar energy enters a structure. The most common mechanisms in passive design are awning and roof eaves. The size of windows and geometry of the eaves and awning determine when sunlight enters. Awnings works well because they can be positioned in the winter to let sun in and repositioned in the summer. Deciduous trees positioned to block the sun or sun rays. For control mechanism, window covering in cold climate require the shade of inside, and in warm climate require the shade on the outside. In the given figure, we can see here all four different directions: east, west, north, south, and some shadow is also there for a particular object. So according to this figure, we can control the solar radiation into the room. Next question comes in mind: how solar building heats and cools? Heat moves from warmer material to cooler one. We know this. Once until there is no longer a temperature difference between the two, thus solar building design lets heat flow from warmer area to cooler area by using the following heat movement and heat storage mechanism. There are two mechanisms for heating and cooling. One is convection and second one is radiation, which I have already discussed in previous in terms of equations. Again, it is a short introduction about the convection and radiation. If I talk about convection, then warmer gases and liquids will rise while cooler liquid and gases will sink. In a house, warm air rises because it is higher than cold air, which sinks. This explains why warmer air accumulates on the second floor of a house while the basement stays cool. Some passive solar homes use air convection to carry solar heat from a south wall into interior spaces. If I talk about radiation, about this heating and cooling, then heat can radiate and move through the air from warmer object to cooler one. To design for warmer weather, passive solar design can incorporate light colored material to reflect incoming solar heat and radiate heat of a building. To design for colder weather, homeowner can use darker material to absorb the sun heat and radiate it into the home. Now the next thing comes in mind, heating and cooling completed. Then how many types of gains can be obtained from a solar? Then there is a two types of gains. One is direct gain, second one is indirect gain. If I talk about direct gain, then the most common and simplest type of passive solar design system is highly required. South facing window are most practical in cold climate, incorporated with good glazing. Thermal mass should be at a minimum of 5 times greater than aperture. We have already discussed about the aperture and window. Next, thermal mass is decided in design process and cannot be estimated. If the floor is the primary thermal mass, it should be dark in color, while wall and ceiling are light in color. The floor will absorb, whereas the wall will reflect. If walls are good for storage, then they should be a dark color. Indirect gain, heat and exterior surface to the living space and use natural form of heat transfer to maintain temperature. These systems include thermal storage walls and thermosiphons. I will tell you what is the thermosiphons later on. Then the second thing will comes in mind, that is Trombe wall. I have given a one figure over here. We can see here what is the Trombe wall and how it can reflect the radiation, convection or heat transfer. So the thickness and conductivity of the wall is critical in Trombe wall. It must be massive enough to absorb and sufficient conductive. In Trombe wall, composed of concrete, adobe or other masonry products. Selective coating on Trombe can improve solar absorption. The wall will prevent the sunlight from directly illuminating the room. Most effective in climates where it has daily sunlight like deserts. So according to given figure, we can see what type of Trombe wall can be constructed in a building or house. Here the thermosiphon. What is a thermosiphon? So a form of indirect gain that relies on sunlight and natural convection to move air without mechanical assistance. It can either warm or cool depending on the system. Solar energy heats an absorbing surface that will warm the surrounding air. The hot air rises, drawing in cold air and creating a convective loop. A closed loop system draws cool air from a building, warms it and returns it to the building. An open loop system draws air from the exterior. A solar chimney will operate on this premises. Now the solar chimney is the best application of such thermosiphon. I have given one figure in this thermosiphon. Here we can see there is some heat exchanger is used for this purpose. Next one is sun spaces. Sun spaces is also required for smart solar building design. Some spaces combine direct gain as well as indirect gain. These may be referred to an isolated system since they are able to function independently. The sun directly heats a space through southern exposures. The space shares its warmth either by conductive, utilizing a wall, or convective currents. Thermal mass or barrel of water help to moderate temperature swings. Due to the construction of room, the structure will experience large temperature swings from day to night, and control may be as simple closing a door. So, sun space is required for buildings. I have given you two figures, daytime and nighttime. Here we can see how the transfer of factor is going on. Now, some solar building design alternatives. Earlier I have explained all the parameters, design steps, pictorial view and other things. Now, what are the solar building design alternatives? So, if I talk about alternative, then there is a 4 different alternatives in this section, like landscape, building form, building component which include walls, glazing, roofs and interiors. And last one is energy substitution. If I talk about landscape, so landscape can be taken by four types like ground reflection, trees, earthworms and structure and underground ventilation ducts. If I talk about ground reflection absorption, then ground surface treatment may be optimized to take maximum advantage of natural daylight and solar heat gain. Light colored ground surface for building with interior daylight controls may be ideal for office buildings. For residential buildings, however, dark color surface immediately adjacent to the windows and light colored further away may be ideal. This combination will take care of winter as well as summer. More natural light will be reflected to the building interior. If I talk about landscape in terms of trees, then the presence of trees leads to reduced infiltration, heat losses in winter, reduced heat gain in winter and summer, and reduce natural daylight. Therefore, trees should be planted in such a way that they provide partial shading of windows during summer. Natural light is not reduced significantly and act as a winter windbreaks. If landscape is for earthworms, then the effect of earthworm structure is that winter heat loss and summer heat gain is reduced. If I talk about landscape in terms of underground ventilation ducts and structure, then the design using buried structure underground pipes may be used to extract earth coolness during summer months. Moisture and odor needs to be controlled and the cool air may be used into building interior for cooling purpose. Now I talk about building forms. Building forms, there are three types of building form existing. One is atrium, second one is configuration and third one is orientation. If I talk about atrium, then atriums or light courts may be on the interior of deep office building and it will lead to enough natural daylight. This will also lead to an increase in building volume. If I talk about configuration, then building dimensions like length, width or height may be proportional to have a minimum energy consumption. A large and narrow building will have a more access to natural light, hence less electricity consumption for artificial light is required. If I talk about orientation of building form, then orientation is a function of building plan, shape, daylighting controls. All major living space such as dining room, study room, living room should face south. The store, kitchen and other utility rooms may be located on north side only. I have given all these three different types in form of figure also. This is the design effect of building form atrium. Here we have reduced the exterior surface exposure to outside air, increased winter heat gains, enhanced summer ventilation and tremendous natural light into interior of the building. If I talk about configuration, then the four different points must be in mind during the design, that heat gain or loss will reduce for reduced surface to volume ratio. Window solar heat gain will increase because of increased south facing surface area. Winter infiltration heat loss will be reduced north side surface area and natural light will increase by increasing south facing surface area. If I talk about orientation, then orientation is also required, like natural cooling and ventilation during summer will enhance. South-facing rooms will have access to direct sunlight and south-facing room will have high winter solar heat. So this is type of building form. Now the next thing is energy supply augmentation. It is also required. Solar water heating system installed at the rooftop of a building will provide hot water as well as shading to the roof, thus reducing summer heating gain and energy consumption. Similarly, rooftop solar photovoltaic system will meet part of the electricity load and will result in reducing energy requirement of the building. So, if I talk about this lecture, then definitely after completing this lecture, all learners must be able to discuss and define components of solar building design, define and discuss about seasonal sun path around the sun, understand the importance of sun altitude when designing, identify 5 components of design and provide example, find direct, indirect, thermosiphon, sun space, Trombe wall and other thing, and learner can explain all these things through some live example where we can incorporate our solar building design concept. So thank you for the listening. Okay, thank you.